Welcome back, everyone. I hope you had wonderful lunch break, and so you're no longer hungry in terms of food, but are still hungry or even hungrier for more exciting information on how to make our apps more performant and efficient. And we finally got to a cloud height, I think. So it's appropriate to continue our event with the talk by Kalyana Chadalavada from Google, who's gonna tell us about Google Cloud Profiler.
Hi, my name is Kalyana Chadalavada. I'm an engineering manager with the Google Cloud Profiler team. Today, my talk is about explaining where you spend your dollars in production. As service owners and developers, we face a lot of difficult challenges in bringing the code from development to production. During development, we have to understand if the code is performing as expected. For this, we need to benchmark the code. There are a number of ways to do this, but finding a right representative workload that closely resembles the production workload is very difficult in most cases. We can try to replicate a production workload, but we can never be sure that we have covered all possible scenarios. Moreover, our benchmarking efforts may be biased and we may not be measuring the right thing. And as a result, we can never fully understand the production performance of a service through benchmarking alone. Now, we understand we have to monitor the performance of our services in production, which poses an entirely different challenge. As developers, it is not sufficient to understand the performance at a high level. We want to attribute resource usage like CPU time and memory to individual code blocks or functions, which helps us to optimize that particular block of code. This understanding is crucial when working with library code that is used across multiple services, like compression libraries, math libraries, or communication libraries. If a bug in these libraries causes your services to consume more CPU or has high contention, the blast radius of this bug could be very large and affect multiple services. In some cases, bugs can cause subtle changes in your performance over time and result in suboptimal resource usage or degrade your performance gradually. Catching these in production is especially tricky. These days, service management is fully automated, and that means services grow and shrink globally in response to real world events and real world workload on your services. This makes it very difficult for service owners to monitor and catch performance issues in a timely manner. Why are we talking about all of this? That's because all these challenges result in making it really difficult for us developers to run our services efficiently and can lead us to spending more resources than we planned on. One way to tackle these challenges is to use continuous production profiling. Google Cloud Profiler is one such product that makes it easy for developers to collect and analyze profiles from production services to better understand the data from your services, has low overhead, and provides actionable data about the service. This approach is battle tested at Google scale and has been in use for some time. The primary interface for analysis is a flame graph visualization. This intuitive visualization instantly provides a bird's eye view of the service resource usage. Cloud Profiler supports 4 languages: Go, Java, Python, and Node.js. And depending on the language, it supports collection of different profile types like CPU time, heap, wall time, contention, or allocated heap. Now, let's see how Cloud Profiler can provide deeper service level insights. On the right is the focus function list. This helps you understand in which functions your services spend its resources. Both self-time and total time for each function are provided. In this example, we are looking at the CPU time profile type for a service written in Go. The list is sorted by total time. The function getMatchCount is at the top of the list with 49% or 3.82 seconds of the time attributed to it and its callees. However, its own self-time is negligible at 70 milliseconds or 0.897%, indicating that this should not be the starting point of any investigation. If you walk down the list in the self column, we can see that the function toLower has 16.5% or 1.29 seconds of CPU time. Sorting by self time will show if this is one of the most resource intensive functions. In addition to examining the service profiles over a specific duration or at a point in time, we can also use the profiler diff mode to understand how a service has changed between two versions or time periods. This can help developers identify performance regressions or confirm that the optimizations they implemented have had the intended effect. The flame graph at the bottom of this slide shows a diff between two versions of a service. Here we are looking at a CPU time profile. The bars in blue indicate that the CPU time consumed in that function is lower than the other profile. The root is showing total CPU time of 315 milliseconds versus 1.4 seconds for a difference of 1.09 seconds, and dropping from 16.8% of total time to about 5%. Now, let's look at a few more ways Cloud Profiler can help developers understand their services better. Some functions can appear in multiple call sites. The default view will show these multiple call sites, but they may get lost in the view and we may not be able to easily locate them, especially in services with a large number of functions and deep stacks. In such cases, we can use the focus filter to reorient the flame graph around a function of interest. The example shown here on the right, we use the focus filter on the function quicksort. As you can see, it shows all the paths into and out of this function, that is, all its callers and callees. Next is the history view feature, which we just announced at the end of September. As mentioned earlier, catching subtle changes over time is very tricky. The history view helps us examine the trends of a function's resource usage over a 30-day period. By default, it shows the historical trends for the top 5 functions of the selected service. You can use show and hide filters to visualize the historical data for functions of your interest. The history view shown here is for heap usage of a service. As you can see, the function with the orange trend line has gone from using 5 to 10% of memory to using around 25%. Looking at the default frame graph may not surface this change in usage immediately unless we use the diff mode with the right parameters or specifically investigate this function. In contrast, history view surfaces this important change in a function's resource usage immediately and helps us intuitively understand when this change happened. The service owners can then look for any new releases or configuration changes made around that time and root cause the issue. Similarly, if a developer optimized a function, they can use the history view to validate that the optimizations they made have resulted in the desired reduction in resource usage. So, using a combination of these features, we can tackle some of the challenges discussed at the beginning of this talk. Let us switch over to a shell and set up for our demo. Prior to starting this presentation, I set up a VM with a sample application. The services in this application are enabled with Profiler. There is a workload generator that continuously generates load against these services. After the presentation is done, we'll switch over to the Profiler UI and look at the profiles that were collected from these services. Now, let's talk about what else we can do with this data. For instance, we can look at this data in aggregate at a fleet level and look for interesting trends. One of the major findings of fleet level insights is documented in a paper written by my colleagues called Profiling a Warehouse Scale Computer. Using fleet-wide analysis, they discovered that a significant amount of resources are spent on a handful of operations. They describe these as the data center tags. Without analyzing continuous profiling data in aggregate, it's hard to imagine that we can understand these macro trends at a fleet level. You can read more about this in the paper that is shown here in the slide. This data can also help us drive cross-cutting optimizations and can have a large effect on the fleet efficiency. And it's especially useful when resource usage in a single function is small enough to evade detection, but has a huge cost when considered in aggregate. I will give an example of one such instance on the next slide. We can also try to understand if services running in one specific zone or location are underperforming compared to others, find outliers, and observe the overall utilization of the available resources. All of this can help us make our services and fleet more efficient and fast. This analysis and discovery is hard, and it's limited by the number of people doing the analysis. And of course, that changes by team level priorities. Teaching someone to do this analysis can be hard and does take a long time to get them up to speed. Now, I want to share a success story from fleet level analysis. While looking for interesting changes, one of the colleagues noticed that the time spent in a tcmalloc function started growing rapidly. The chart here shows total compute resources spent on this function. You can see that the CPU usage has more than doubled. The issue was root cause to loss of tail call optimization and was promptly fixed. You can read more about this issue and the fix in the LLVM review shown here. The chart shown here shows the trend and not the actual values. This is one example of where fleet level analysis of continuous profiling data can be very helpful. Now it's demo time. Let's switch over to the Profiler UI in Google Cloud Console and see the profiles collected from the sample application I started earlier. Here we are in the Google Cloud Console homepage. Locate the Profiler entry in the Operations section of the menu. Let's check for what all services we have profiles available. We see about 7 services here. Let's load the front-end service. By default, CPU time profile type is loaded. Just by looking at the flame graph, we can see there are 5 or 6 distinct stacks shown here. Let's examine the focus function table. We see here that the list is sorted by self-time. We see most of the self-time is attributable to the syscall function. Click on the function name to focus the flame graph on this function. Here we see all the paths coming into and out of this function. So we see 1, 2, 3, about 7 or 8 different paths into the syscall function, and only 2 paths out of this function. Let's dismiss the focus filter and open the focus function list again. This time, let us sort by the total time. We see that the function internet socket is at the top of the list. However, its own self time is negligible while the total time is significant. This indicates that most of the time is attributable to its callees. Let's click on this function name to focus the flame graph on this function. So we can see there are 2 paths coming into this function and several paths out of this function. We also see that syscall appears as one of the children of this function. Let's go ahead and dismiss the focus filter for this function. Since the services were running for a very short time, the history view won't show any interesting trends. Let us see what other profile types are available. Since this service is written in Go, we see 5 different profile types. Here is a heap profile type. And here is allocated heap profile type. Let's open a different service. And we see allocated heap profile type for the service user. And here is his CPU type profile type. Let's see how much code I had to add to enable profile collection and get all this useful information. Let's switch over to the terminal. First, we add an import path for the profiler co-agent. Then, as early as possible in the main function, we add the agent initialization code. So that's about 4 lines of code. And that is all what is needed to enable profiler in any service. The effort is similar for other supported languages as well. Since profiler uses a sampling mechanism, the effective overhead of profile collection on your services is negligible, and it reduces as the number of instances of your service increase. And that concludes my talk and demonstration of Cloud Profiler. Thank you for listening. And many thanks to Taras for giving me the opportunity and continuing to organize this summit despite the unusual circumstances we find ourselves in. Thank you.
Thank you so much, Kalyana. It's a fascination of mine, the profilers. It's really awesome stuff. I'd like to remind everyone that if they have any questions, they can ask them on the Slack channel. And since we currently don't have any, I'm going to go with mine. So I'm curious if you have any plans to lift the level of abstractions for the kind of insights you provide to make them a little bit more actionable and maybe more like a push based, where based on your analysis and maybe historical data of performance trends suggest that, oh, like there is this, it looks like there is a regression in this function and it's probably been caused by this and this, and you can probably try that and that. Do you have any plans for that?
Yeah, we are working on something similar, but as you know, trying to root cause a change to a particular change in the code is actually a pretty difficult problem. We've been working at it for a while. I think we'll be introducing some new features shortly, which are in line with what you just mentioned, moving away from sort of having people come and analyze the graph and look for opportunities for optimization into maybe, providing some alerts saying, hey, something has changed in your service, why don't you come take a look? So yeah, that is something we are working towards.
And do you already have APIs that exposes data for things like, for example, maybe IDE, where as part of your editing experience, it would be pretty cool if you could just see some visual cues for every function. Like, for example, when you open a certain function, it could be highlighted as like red based on the fact that it's like a hot function, for example. Or when you call a function, you can mark it with some extra color or whatnot to identify that it's using I/O or some other blocking operation, so that clients, developers, when they call those libraries or functions, they are aware of the performance implications that may be associated with the particular call.
Yeah, that's a really good point. And we actually have that for our internal IDEs and on the internal infrastructure. It automatically annotates the hottest functions. So when you're actually editing it, you can see which functions are consuming how much. However, on the internal infrastructure, we have pretty large quantity of high quality data. So making that is actually quite easier. Bringing it to Cloud Profiler is something, we'll be working towards. We had a few discussions about that. For Cloud Profiler, the main thing is it's driven by user demand. So whatever users request the most is what we put our efforts on first. But that is something we've been thinking about for some time. If there is interest, I think that's something we'll definitely work on. There's also a second problem there, right? Like we can make probably the APIs available, and whoever are working on the IDE integration can probably call that and sort of have data available. But if we have to own that as well, then that becomes a little bit more complicated because there are too many IDEs to support.
Well, that's convenient that we now have a language server protocol. And I believe that maybe if all the companies could collaborate and come up with a good standard for providing this sort of performance information, I think it would be super useful, because we are definitely exploring these kind of things internally at Facebook, because we also have a lot of profiling data, and we would love to bring this information in the most useful way to our developers. And IE seems like a very reasonable place to do it, just because, first of all, you get this information before you even add a regression, and second, it's just the editor where we spend most of our time. So I guess it's just a very natural place to put as many signals as possible.
Yeah.
And one more question, I guess the last one from me would be that, like, have you thought about using this profiling information as some sort of a PGO type of thing, where you can use this to, for example, change the layout of the binaries automatically based on the historical data and whatnot?
Yeah, we do that as well, just not with Cloud Profiler. I think there are a few published papers and talks that some of my colleagues did on using the fleet-wide profiling data for LTO and PGO.
But do you have any plans to support this in the future for cloud profiling?
For that, the main challenge is we have to control the entire tool chain, right? We'll have to, whatever compiler users are using, wherever they're building, they should be able to ingest the profile format that we publish. And our profile format is pretty open. The proto is available on pprof GitHub. So if there are any collaboration opportunities, we'd love to work with the community in making that happen.
Awesome. Well, thank you so much, Kalyana, for your time and participation. Amazing talk. Really love that. So have a wonderful rest of the day. I also hope that you can, maybe if you'd like to, you're very welcome to join us for the panel discussion at around 4 p.m. That would be awesome.
Yeah, I'm looking forward to it, and thank you very much for the opportunity.